formulas, I mean the conditions have been given, the constraints have been given. Okay, by using the formula what we used in the last class here, I'll show you those numericals. Yeah, here. So we have this formula similarly to what I have there, and then you have the limits. This is second generator what we used in the initial condition, right? This is the total demand. Okay, what we do is we take a partial differentiation of this. When you take a partial differentiation of this, you will get this equation. Okay, and that equation, when I try to equate, we will equate it to lambda. Fine. So when I solve for only for pg1, we get this format of equation. Okay, lambda minus 6 by 0.012. At least this much you can understand, Uday. So
yes, sir.
Yeah. Now I have already came to that point here. Like you can see here pg1 lambda. I have an equation here. Okay. So for similarly for all four, I have the four equations. Okay. Losses again are neglected. Demand is 700 megawatt. I'm sorry. Yeah. So I'm sorry. So the purpose is not merely to make the arithmetic larger here. Okay, including 4 generator. The main intention is, the purpose is to demonstrate that the method does not fundamentally change when the number of generator increases. Each generator still has a cost function of its own. Each cost function still gives you an incremental cost equation. Incremental cost equation is when you partially differentiate it. Why? Because incremental cost means you have a cost for the generation for certain load. If you increase beyond that, there is extra cost which gets added. Losses will also get, if losses are considered, losses will also get included. That we call it as a penalty factor. Lagrange things comes in, then we have a penalty factor. Those are the few things we discussed in yesterday's class with the numericals also. You can go back and refer the recording. Well, so incremental cost, I mean each cost function still gives us an incremental cost equations, and each equation can still be inverted in terms of lambda. That's what we have tried here. So if you have 4 generator also, you can do that. If you have 7 generators also, you can do that. See, for unit 1 differentiation gives us here g1 is equal to 0. From here, okay, PI-G1, if you want me to write that, I'll just choose the pen. Yeah. So for the first one, if you have to differentiate that, you will have df1. You can make it as f1, f2, f3 for each one of the generator. So df1 divided by dpg1. We are differentiating it with respect to dpg1. The differentiation will give you 0.008 pg1 plus 7, right? This is what you are going to get. So now we have the formula. The formula is the formula basically means, pg1. If you want to substitute for pg, this we have to equate to lambda value. Okay, so if you want to solve for pg1 from this equation, from the above equation, this becomes pg1 is equal to lambda. This comes this way, right? Minus 7 divided by 0.08. Same thing you have here, right? Well, so very similarly for unit 2, unit 3, unit 4 also you have there. We now have 4 lines whose output depends upon the same lambda. Lambda is not changing. You can see that I don't have lambda 1, lambda 2. The lambda is the same thing. Okay. So before solving it is worth looking at the intercepts. See, unit 3 begins at the lowest marginal cost, followed by unit 2, unit 1 and unit 4. Okay. And yeah. But we should not interpret this as a meaning that unit 3 alone should carry the entire load, because it is starting with a very minimal cost. Okay. So the slopes are different here. So the marginal cost rises at different rates as the output increases. So economic dispatch continuously redistributes the generation so that the marginal cost becomes equal to the optimum, subject to limits. For 700 megawatt demand, we need a lambda that makes 4 outputs add to 700 megawatt. We can choose a low and high trial, that is the two trials we choose. One I'll show you in the next slide. Because you don't have any other option to identify lambda, you have to choose in the sense this is an unknown character here and this is an unknown character. You have unknown characters both on LHS and RHS, so you can't just go on solving this, you have to assume somewhere. So we will assume the lambda value, one we call it as a low, another one is we'll call it as a high. That is what we discussed yesterday as well. So low and high trial rather than trying to solve the complete equation blindly here. So in the next slide, it will show you the numerical search. The fact that 4 generators are present changes the arithmetic but not underlying logic of ours. You can see here what we do, we will choose lambda first we will choose, okay, this we are choosing, okay, lambda we'll take it as 8, okay, you get PG1 125 with the same formula. You solve for lambda here as 8, okay, you will get 1 upon 0.08. Yeah, if you get 1 upon 0.08, the answer will be, if you have calculator, you can check. I have a ready answer 125 megawatt. You can cross verify as well. Okay, so you have got 125 here. Similarly, for the second one also you get 125. Third also you are getting 125. Fourth you are going to get 50. But the total is 425. When you combine these two will become 250. 250 plus 125 is 375. 375 plus 50 is 425. You are not meeting the load. You are not meeting the load, right? So this is too low for you. You can't choose 8. So what you will do, you will go for 9 now. When you choose 9, PG1 itself will give you 250 megawatt of generation, 208 megawatt, 185 and 150. And total will give 795. You want 700. This is high. 95.8 megawatt generation is high. So this is too high. Okay, then we try to solve for lambda. You will get to know that lambda will come in between these two now, 8 and 9, right? So you will have this interpolation also. Okay, then you get this lambda. How you get this lambda? Lambda is equal to 8. This is the formula what we are using. Okay, here you have the least count, here you have the highest rate. I mean, what is the too high rate, and you have the too low rate. Okay, so if you use this formula, you will get the exact lambda value. So when you calculate the same equation with the exact lambda value, you will get your load. This will give you at what ratings each of your generators should run. Okay, you have 4 generators here, so converged, right? This is how we solve it. Okay, and now you take these values back to the numerical and see, this is the limit you have, upper limit and higher limit. Okay, so in the generator 1 is 217.7. this is well within the limit, no problem. This is 186.8, 80 to 300, well within the limit, no problem. 171.4, it is again well within the limit, no problem. And the last one is 124.2, again this is well within the limit. Okay, so no problem, all the 4 generators can operate in this operate in this range. Okay, so this is the entire explanation here. Okay, so the interpolated value lambda is equal to 8.7416 lies between these two trial values. Substituting it gives the approximately, we have 217, 186, 174 and all. Adding them we get 700 megawatt. The result is then checked against all 4 generator limits also, right? Every output lies within its permeable range. No active limit correction is required here. If anything goes beyond also, we call something as active limit correction. Yesterday we tried with one such numerical also. Okay, so the total cost calculation is the final verification. We evaluate each generator's cost function as it is assigned output and add the 4 hourly costs to obtain approximately, here it is, you can see. So here you have these values, hourly cost values. Okay, rupees total cost is here. Okay, 201674146313 per hour. Total cost per hour of generation is 6479, right? This gives us 2 different outputs from the optimization. Someone wants to join. So uh, yes. So the total cost calculation is the final verification we evaluate each generator's cost function as it is assigned, right? So this gives us two different outputs from the optimization, the dispatch itself and the operating cost associated with that dispatch as well. So the deeper lesson is scalability. The four generator system may look sustainably more complicated than the two generator system, but computational structure remains one dimensional in lambda because lambda is same for all four generators. In larger practical systems, the numerical implementation is automated, but the engineer's understanding remains exactly what we are developing here. Each lambda corresponds to a complete candidate dispatch, and correct lambda is the one that satisfies the system requirement while representing the respecting the feasible operating region. Okay. So using the same four generators from the last worked example, rerunning lambda iteration at three different demand levels will show the merit order in action here. Okay, and cheaper units are always loaded further before the expensive ones. Okay, so here now this slide actually changes the question from what is optimum from one load level to how does the optimum move when load changes. So we have different loads now. We calculated for 700 load in our previous case, we had all these things, right? But if load becomes 500 megawatt, if load becomes 900 megawatt, then how exactly it's going to respond? See, that is a much more useful engineering question because a power phase system does not operate at one fixed demand always, right? Because power system, I mean, as at least mentioned here, you have 500, you have 700, you have 900 megawatt cases. Are the three snapshots of the same generating fleet again? You are using the same 400, four generating generator fleets. What we have here, these four, right? We are using the same four generators, but load is changing. As you can see, the demand was 700 megawatt here, which is going to be 500. Load fluctuation is very much acceptable, right? So it might go up to 900, who knows, right? So all these things have a bigger impact. Okay, so well, so at 500 megawatt, as you can see, lambda value is 8.20 rupees per megawatt hour, but at 700 it is 8.74, and at 900 it is 9.82, right? Megawatt. This upward movement of lambda is the numerical expression of increasing marginal system cost. As demand increases, the system must move further up generator's incremental cost curve. The next megawatt therefore becomes progressively more expensive for us, isn't it? So the generator output does not increase by the same amount here. From 500 to 700 megawatt, unit 1 rises 67.4 megawatt. As you can see here, here you have the difference of 67.4. Here you have a difference of 44, 45 nearly. And here you have somewhere around 32, 33. And here you have 54 kind of, right? Yeah, exact 54. So each generator is raising its own limits and they are not uniform, they are different. So the additional 200 megawatt is therefore distributed according to the slope of the incremental cost curve there, not divided equally among the, like you have 200 more, you have four generators, it's not 50 50 50 50 megawatt per generator. It's not, that's not work in that way, right? So this is exactly what economic optimization means in operational terms. This also explains why marginal generator is so important in electrical markets. So the system's marginal cost is associated with demand. As the load moves upwards, the marginal condition moves along the aggregate generation cost curve. So the table therefore connects the mathematics of lambda iteration to the broader ideas of merit order and marginal pricing. Just a moment. See, when we think of Indian power sector case studies, connects merit order to operational practices. So the central economic idea is familiar. Available generation is economically ranked according to the variable costs, and the system must meet the demand while respecting technical and network constraints. So the actual control room is much more complicated than a hand calculation. So load forecast, generator declaration, renewable availability, outages, network constraints, market rules, and security requirements are all influence the final schedule here. See, renewable generation provides a useful modern example. Solar and wind have a very low short-run marginal cost because there is a no conventional fuel expenditure for each additional megawatt generated. But when available and technically deliverable, they can therefore appear at the low cost end and merit and end of a merit order representation. So, however, long marginal cost does not guarantee unlimited dispatch also. Transmission congestions, system security, balancing requirements, curtailment can restrict the outputs as well. So, the larger lesson is that economic dispatch is always embedded in physical systems. The mathematical model tells us economic directions only, okay, while operational constraints determine what is actually feasible. So Indian context also illustrates the why economic dispatch cannot be separated completely from market and regulatory arrangements. The mathematical principles of merit order may be common, but the way schedules are declared, accepted, revised, and settled depends upon the institutional frameworks. A control center must work with declared generator capabilities, forecast outages, network security informations. So the economic model therefore becomes one component of a larger. Give me a second. I'll just switch on my AC. So, well, the way schedules are declared, accepted, revised, and settled here depends upon the institutional framework. A control center must work with declared generator capabilities, forecasts, outages, network security informations. The economic model therefore becomes one component of a larger operational decision here. See, the case studies also highlights the difference between a mathematical merit order and an operational feasible schedule, right? A generator may be cheap but unavailable. A renewable unit may have zero fuel cost but be limited resource availability or transmission congestions. Thermal unit may be expensive but required for system security, right? So the real dispatch problem, therefore, always contains more information than a simple cost ranking there. When we look into this ELD actually runs economic load dispatch. See, economic load dispatch not normally a calculation performed. Who wants to join now? No one. Okay. So is normally is not a calculation performed once in the morning and then forgotten. Operating points of the grid changes continuously. Demand changes as consumers switch appliances. Industrial loads vary. Weather changes. Renewable generation rises and falls, and generator availability changes. Therefore, the economic set points must be repeatedly recalculated here. It is useful to distinguish three time scales. One we call it as unit commitment operates over much longer origins and decides which generators are available or switched on. Okay. Then you have economic dispatch determines how much power each committed generator should produce. Then you have automatic generation control then operates much faster, adjusting generator outputs around their scheduled values to maintain system frequency and interchange targets. These are related but distinct layer of control. The reason a specialized dispatch method is attractive is its speed. Okay, classic lambda iteration exploits the structure of the quadratic cost and can reach the solution with a very few well-chosen numerical steps. In the simple textbook case, the practical advantage is not that modern optimization is unnecessary, but that a specialized method can be extremely efficient for a narrow problem it is designed to solve. So at the same time, we should not overgeneralize the textbook iteration count. Real dispatch with network constraints, non-smooth cost curves, ramp limits, prohibited zones, losses, and changing operating conditions may require more sophisticated algorithms. The correct The correct lesson is that lambda iteration is an efficient solution method for a particular economic dispatch structure and not a universal solver for every power system optimization problems. See, moving ahead, I really want to name this as an textbook lambda iteration model assumes that generators can move freely to whatever the output the optimization recommends. But real machines cannot always do that. The first complication is ramp rate limit. Okay, if the generator was producing 100 megawatt in the previous interval, and it is allowable upward ramp is 10 megawatt per interval. Okay, a newly calculated set point is 150 megawatt cannot be reached immediately. The generator can move only to 110 in the next interval, and gradually in five intervals it will reach up to 150. So until it reaches its uh, five intervals, what about the scenario, right? So prohibited operating zones create a different problem. A generator may have a range of outputs that should be avoided because mechanical vibrations, boiler limitations, or other equipment constraints. The feasible set then becomes discontinuous rather than one continuous interval. A simple formula, what we discussed just now, may produce like PGI lambda is equal to lambda minus BI divided by 2AI, the same formula, may produce an output inside a forbidden region there, requiring more specialized treatment. So, must run units illustrates another important distinction between economic preference and system security. A generator may be required to remain um, I mean, and online because of voltage supports, reactive power requirements, local reliability, control obligations, or other operational considerations. So its output may therefore be determined partly by system constraints rather than by its fuel cost alone. Finally, we will have the talk of losses. See, losses are not calculated once and forgotten because losses depends on the dispatch. Changing the dispatch changes the loss. Changing the dispatch changes the loss, which changes the required generation, which changes the. This is why realistic loss inclusive dispatch may require several outer iterations. The clean two-pass example is intended to teach the mechanism, not to claim that every real network converges with exactly two passes. Please do remember that. Okay. So merit order dispatch, when you look into the merit order dispatch, the merit order idea provides the bridge from mathematical exercise to actual system operations at its simplest. Generators are ranked according to the cost of producing the next megawatt and the system loads, the available generation in an economically sensible order until demand is met. Lambda iteration gives a continuous mathematical versions of that idea for quadratic cost functions. In the Indian context, operational picture is more complicated than a simple classroom merit list because actual scheduling and dispatch must consider a declared availability, technical minimums, ramping capability, transmission constraints, ancillary requirements, market rules, and system securities. All these things are involved. See, the important connection to today's topic is that economics signal still depends strongly on marginal operating cost, on which generating resources are available to respond. Renewable generators such as wind and solar often have a very low short run marginal cost. Once they are available in a simplified merit order picture, they therefore appears near the bottom of the marginal cost stack. Their presence can reduce the dispatch or higher marginal cost thermal generators during period of high renewable availability. But the real system cannot simply treat every renewable megawatt as a unconstrained network congestion, forecast uncertainty, curtailment, and system security requirements can alter the actual dispatch there. So the key engineering lesson out of this is that an optimization algorithm can only be as good as the information and constraints applied to it. If declared capability is inaccurate, cost data are wrong, or network conditions are not represented properly, then the calculated dispatch may be economically attractive on your paper, but when you try to put it operationally on a real time, it's very inappropriate. So where do we merit order is used here as the economic core. Actual Indian grid dispatch also incorporates network security, availability, contractual and regulatory constraints to a considered to an good example. I mean, a good level. So what we learn out of this point is that uh, it actually consolidation of the practical side of the method, the brackets and interpolate procedures does not depends on having exactly two generators. What changes with the system size is the amount of arithmetic, okay, not the underlying idea. Idea remains very same. Every generator contributes to a response to lambda, and the total response is adjusted until it satisfies the required generation. So the merit order interpretation follows directly from the incremental cost curve. Generator with lower marginal cost tends to mm, take more output, but their output is not increased without limit because their marginal cost rises with generation and because physical limits eventually become active. So the time scale point is also important. Economic dispatch belongs between longer and horizon commitment decisions and faster frequency control actions. Finally, real-world constraints such as ramp rates, prohibited zones remind us that the clean, continuous mathematical model is an approximation of much richer physical systems. So, when we come out to the limits and losses, we can now combine two major complications introduced in this session: generation limits and transmission losses. Neither one replaces the other here. Generators may hit a limit while the system is also losing power in the transmission network. So the practical algorithm needs to handle both effects simultaneously. The natural structure is nested iteration. The outer problem is loss estimate. We begin with the estimate of loss, okay, we call it as a PL. Initially, perhaps it's zero. The estimate determines the total generation target PD plus PL, that is demand plus loss, right? Inside the target, we solve the economic dispatch problem using lambda iteration. During that inner solution, any generator that violates its limit is fixed at the appropriate boundary, and remaining demand is redistributed among free generators. Once the inner dispatch is obtained, we calculate a new transmission loss from the resulting generator output. Okay. If the new loss differs materially from the previous estimate, the generation target changes and we repeat the inner dispatch. Eventually, the loss estimate and dispatch becomes mutually consistent. At that point, the outer loop has converged, right? So the five practical building blocks on this slide, what you are seeing here, are therefore worth remembering as a sequence here. See, invert the incremental cost equation, bracket or solve for lambda, clip the active limits, account for penalty factors or loss effects, and recalculate losses until stable. A modern software implementation may look very different internally, but these are the ideas represented by the classical formulation. So, see, here you have a revision table. So, the revision table is useful here because it shows how the individual worked example are not separate topics here. See, when you look into the worked example 1, it establishes the difference between the total cost and the incremental cost. When you look into the worked example 2, it introduced the penalty factor. When you look into the worked example 3, it demonstrated the basic lambda iteration search. When you look into the 4, it added an active generator limit there. When 5 added the transmission losses, while 6 demonstrated the same approach scales to 4 generators. See, if these examples if examples are understood as a progression, the method becomes much easier to reconstruct from the first principle. When there are no limits and no losses, equal incremental costs are enough. When limit binds, the constraint generator is fixed, and the free generators continues to equalize the marginal cost. When the losses appear, the marginal condition is modified by the penalty factor, and the losses estimate must be updated here. This progression is more important than memorizing the numerical answers. The numerical values such as lambda 7.629 or lambda 7.2 belong only to the particular data set in the examples. You no need to recall them. What I want you to remember is the progression. So the reusable knowledge is what we call is a procedure that generated them in an examination, or even in your engineering calculations. A correct procedure with transparent verification is more valuable than remembering an isolated final number. Okay, so we are moving to the final deck of these things. This is the what lambda iteration does not decide. See, this is the very heading says, as you can see here, this heading, it actually draws a boundary around the economic load dispatch, what it can actually decide. Throughout today's calculation, we quietly assumed that set of generators already running was known. We decided the output levels of those generators, but we did not decide whether generator should be started or stopped. That distinction matters because starting a generator, it introduces some cost, right? Time dependent constraints, right? Suppose we will think of unit 3 has a high startup cost but a low marginal fuel cost. During short period of low demand, it may not be economical to start it, even though yeah, well, say coming in admitting will disrupt my flow, man. What I was explaining, excuse me.
This one, sir.
Huh?
Lambda iterations.
Lambda iterations. I was not talking about lambda. I was talking about low start. I mean high starting cost. Like when I was trying to give an example of unit 3, like it is, if it is having high starting cost and low marginal cost, and in between at an interval, if I want to start it, it may not be economical to start, even though once it's running it would be one of the cheapest generators. Simple single period lambda iteration calculation cannot represent that startup decision because startup cost and on and off status are discrete and time coupled. So unit commitment therefore sits at the next level of the problem. It decides which unit are committed over a sequence of time intervals while considering the minimum up and down times, startup costs, shutdown costs, anticipated demands. Once that on off schedule is known, economic dispatch can determine the megawatt output of the committed units at each intervals. This is why today's method is not discarded in the next session. It becomes the inner dispatch calculation inside a larger scheduling problems, and unit commitment layer decides the feasible set of generators for each hour. Okay, so lambda iteration then solves the continuous dispatch within the that set. So what you learn from here, at this point, the whole session can be reconstructed from our original optimization problem. We start with the cost functions for each generators, derive the incremental cost, impose the power balance constraint, use lambda as common marginal value. Generator limit turns some of the variables into active constraints. Transmission loss modifies the marginal relationship through the penalty factor. Lambda iterations provides the numerical mechanism for finding the dispatch. The formula, what we discussed here, also it is given here, which gives you the bracket is computational heart of the no loss quadratic cost problem. It is obtained by differentiating the cost function and equating the marginal cost to lambda. The moment a generator is constrained, however, that formula may predict an infeasible point. So the generator must be fixed at its limit and removed from the set of free variables. With losses, the loss estimator enters the power balance and the penalty factor modifies the marginal cost conditions. The resulting procedure is no longer simply one algebraic calculation, it is an iterative consistency calculation between generation loss and economic marginality. Finally, today's economic load dispatch is one layer of the larger power system optimization hierarchy. Unit commitment determines which machines are available. Economic dispatch determines how much each available machine should produce. Network aware optimal power flow adds voltage, line flow, and other electrical constraints. Here is a formula sheet. This will help you. Anyways, I'm going to share this with you. Okay, the entire formula sheet you have here. The formula sheet should not be treated as a list of memorized independently, as I was telling you again. Each expression has a clear origin. The quadratic cost function is a mathematical approximation of measured generation cost, right? Differentiating it gives incremental cost. Setting the incremental cost equals to lambda gives you the inverse dispatch equation. We have gone through the B coefficient expression represents the approximate network loss model. Differentiation of that expression gives the incremental loss used in the penalty factor. The interpolation expression is simply a numerical shortcut for locating the point where the aggregate generation response crosses the demand. The binding limit rule is the optimization interpretation of an active inequality constraints. Seeing the formulas as an connected chain is much safer than memorizing them as an unrelated equations, right? It's pretty simple how you can dwell out of this equation. Okay, so simple. I mean, but the thing is, you need to know how what are they related to. This is the generator's operating coefficient, operating cost function, which will be given. If you differentiate, you'll get incremental cost, and you have inverted lambda iteration. You can obtain by equating the same equation to lambda. Okay, you can get this equation. Okay, this is the loss formula you have to remember, and if you have a partial differentiation you'll get an incremental cost, right? And this is the penalty factor. Once you have the calculation of this, the same thing will be used here. So all these things are very much connected. Okay, here you have the penalty factor included for unconstrained units, right? Here you can find out the interpolation for lambda, that is you have lower lambda what you have assumed, and you have a higher rate of lambda what you have assumed. Then you have the difference. Delta P1 is the lower limit, delta P2 is the higher limit. By utilizing this, you can calculate the exact lambda value. Likewise, that is actually a link where you can really establish that link. And who wants to join now? This is mockery of the class, I will tell you. Well, These are the practice problems. If you want, you can practice them. Up to you. I have given you three practice problems. This is a bit of sensitivity context really I want to discuss here. That is, fuel price sensitivity gives us a useful economic interpretation of the coefficient in the cost function. If the fuel price of a generator increases, its marginal cost increases for sure, right? In the incremental cost graph, this is represented in the simplified model. By shifting the generator's line upward at a fixed lambda, the intersection therefore moves towards the lower output. But the system cannot simply allow the total generation to fall there, right? If one generator become more expensive, other generator must take more of the load, and the common system lambda generally changes. In the simple worked example 3 structure, okay, increasing B1 from 6 to 7 rises units once incremental cost from rupees 1 megawatt hour at every output. If you want to go back and have a look, so the new optimum therefore changes both lambda and distribution of generation. This demonstrates why merit order is not a permanent ranking carved in a stone. A generator can move from being relatively cheap to a relatively expensive when fuel cost, efficiency, availability, or other operating conditions comes into picture or changes. Economic dispatch, therefore, is a repeated optimization process, not one-time classification of a generator. So lambda iteration versus every other method, uh, what we have discussed in this entire module. If you have a look, this is a beautiful comparison. The slide places lambda iteration inside the border toolkit developed in this course. Simplex methods are natural for linear programming formulations such as piecewise linear cost models. Lagrange and KKT methods provides the theoretical optimum conditions for nonlinear economic dispatch and explains why marginal cost equalizes. Dynamic programming addresses discrete multi-stage decisions such as unit commitment. Lambda iterations exploits the special structure of the quadratic economic dispatch for a fast numerical solutions. See, we have Newton-Raphson method and optimal power flow solve a different level of the problem because they represent the electrical network explicitly. Economic dispatch may treat the system as a collection of generators connected through a simplified balance, while optimal power flow incorporates bus voltages, angles, line flows, reactive power, and network constraints. Therefore, no method is simply better than every other method. The correct choice depends on the problem formulation. The distinction is central to power system optimization. The mathematical method should follow the structure of the decision problem. Continuous convex dispatch with a quadratic cost is highly amenable to lambda iterations. Discrete scheduling requires methods such as dynamic programming or mixed integer optimizations. So network aware dispatch requires OPF formulation, understanding the problem because choosing the solver is itself an important engineering skill. See, lambda iteration is particularly suited to smooth quadratic cost economic dispatch. More general EMS and market implementation may use other numerical optimization methods when additional constraints are present. So the next is unit commitment. Anyways, I'll jump to the unit commitments very soon now. I'll not waste any time here. Okay. Uh, we'll move to the unit commitment. Well, so we had a very detailed class about the load, economic load dispatch and all those things. Now we shall move with the unit commitment, dynamic programming and optimal generation scheduling. Okay. So what are we going to learn throughout this session? Agenda I'll read out. I'll try to finish it off today itself, even it's extends, no problem. Okay. So, uh, so unit commitment. Today's session begins at a point where the mathematics of economic dispatch is already very much familiar for you. But operational decision has been larger. Until now, one set of generator was assumed to be available and running. The central question was how the required power should be divided among them. So unit commitment moves from one level above that question now. Before calculating the megawatt output of a unit, the operator must decide whether that unit should be running at all. This is a major shift in the nature of optimization problem. The earlier dispatch problems were dominated by continuous variables such as generator output. Unit commitment introduces a binary decision, yes or no kind of. A generator unit is either synchronized and available to carry load, represented by value of 1, or it is a shutdown, represented by 0. So the consequence is that the problem becomes mixture of continuous and discrete decision making, and decisions made in 1 hour influences what is possible in later hours. So sorry. So here we develop a unit commitment from the basic physical reason for switching units on and off through the costs and constraints that counts the decision, and finally uh, to a dynamic programming solution. So objective is merely to obtain an answer for a single hour. It is to construct a schedule. It is to construct a schedule over a sequence of hours and to identify the least cost path through the sequence. This opening material should be read as the frame for the complete session. The later numerical work is easier to follow when hierarchy of decision is kept in mind. Commitment first, dispatch second. Okay. The mathematics becomes progressively more detailed, but every later equation returns to the distinction between deciding availability and deciding output. Okay. So I don't think this actually matters. See, from session one through four, 1 to 4, built up, uh, machinery of economic dispatch. It is before we get into unit commitment, it is important as to preserve the connection with the previous ones. Economic dispatch remains completely relevant if two or more generators are already committed. Their outputs are still selected by the familiar economic principle that the unconstrained unit should have a equal incremental cost. If I want to explain the same thing in mathematical form, the marginal cost of the committed generator is coordinated through the system multiplier lambda there. So the previous sessions are extended this condition when transmission losses were included. If you remember, a generator that is electrically removed from the load center may require a larger change in generated power to produce the same effective increase in the delivered load. The penalty factor therefore modifies the upper and marginal cost. None of these mathematics disappear in unit commitment. Instead, it becomes an inner calculation. First, unit commitment chooses the units that should be on. Then, economic dispatch determines how those on units should share the load. This distinction can be stated very clearly. Economic dispatch answers, given the running fleet, how much should each unit generate. Unit commitments ask the earlier operational questions: which members of the fleet should be running in each hour. The two problems are therefore hierarchically and tightly connected here. The commitment decision determines the feasible set of economic dispatch, but economic dispatch then determines the minimum production cost associated with a particular commitment decision. A useful operation analogy is to separate permissions from allocation. When you talk about unit commitment, grants a generator permission to participate in the next operating period by bringing it online. Economic dispatch then allocates the actual megawatt share among the permitted generators. This explains why an economic dispatch result cannot be computed meaningfully for a unit that is not committed yet. Its operating interval does not exist in the current feasible set. As simple as that. So, the opening material should be read as the same frame for the complete session. The later numerical, will be easy for you. Uh, Let me have a quick 5 minutes of break if you don't mind. I'll just have some water and I'll come back, and then I'll continue with the class. Is that okay?
Okay.